The civilization was in despair. They had exhausted every possibility. They had constructed vast observatories spanning entire galaxies, capturing every wavelength of light emitted from across the observable universe. They had designed brilliant instruments to probe the microscopic, then the subatomic, and eventually the quantum realms. They had even expanded their reach, colonizing immense stretches of the cosmos, their great arc ships traveling between galaxies over billions of years. Without a doubt, they were the most advanced civilization the universe had ever known, yet it was still insufficient. After countless millennia of relentless pursuit, they reached a profound realization. Their universe was not alone. There were infinitely many others. What they once perceived as an unfathomably vast cosmos was merely a minuscule bubble, adrift in an endless, boundless expanse. This revelation did not disturb them. Having long since transcended their biological origins, they were accustomed to the harsh indifference of the universe. The real dilemma lay in measurement. The existence of an infinite multiverse introduced overwhelming challenges, particularly when it came to assessing probabilities. A seemingly simple question, such as whether they were alone in the cosmos, was straightforward in an observable universe. They could determine the answer by meticulously scanning every star and galaxy. However, even after uncovering methods to access other regions of the multiverse, they discovered that these parallel universes were not merely numerous, they were infinite. And with infinity came an impossible predicament. Probability ceased to function. Was their universe common or rare? Was their form of carbon-based life abundant, constituting 5% of all life in the multiverse, or an anomaly, representing 95%? The question was meaningless when faced with an infinite number of universes. Every percentage in their calculations registered as zero. How many intelligent civilizations existed across the multiverse? An infinite number. But the multiverse also contained an infinite number of empty, lifeless realities. No matter how much data they collected, it amounted to nothing. Despite their eons of effort, they remained completely ignorant. Their quest had begun in the distant past, when their ancestors first ventured into space, sending probes and constructing grand observatories beyond their homeworld. Over time, they developed their own Kardashev scale, mastering the energy of their planet, then their solar system, their galaxy, and beyond. Ages passed, and they reshaped entire planets, star systems, and galaxies into colossal experiments and intricate laboratories, simultaneously peering outward into the vast cosmos, and inward into the fundamental nature of reality. But how far could they truly go? How much knowledge could they ever acquire? Were there cosmic thresholds they could never cross? Hidden truths they could never unveil? What were the ultimate limits of understanding? In 2011, nomadic travelers in the Sahara Desert stumbled upon a tangible fragment of Mars. This meteorite, designated Northwest Africa 7034, harbored a remarkable secret, one reported by multiple news sources. However, in today's media landscape, where information is overwhelming and often conflicting, determining what to trust can be a challenge. This is where Ground News proved invaluable. Their platform consolidates global news, allowing for comparison of coverage and verification of facts. Through Ground News, I discovered that this Martian meteorite provided evidence of water on Mars over 4 billion years ago. The ability to cross-reference this finding across numerous reputable sources, conveniently summarized in bullet points, made it easy to grasp the key details at a glance. Each news source on Ground News is also tagged with insightful contextual details, its political alignment, ownership, and credibility rating. Notably, over 90% of the sources reporting on this discovery were rated as highly factual, minimizing sensationalism and bias. If you want an efficient way to stay well informed on any topic, I encourage you to visit ground.news/HOTU or scan my QR code. It all began with patterns. Long ago, the creatures of the civilization observed recurring rhythms in their world. The changing of seasons followed a predictable cycle. Dark clouds on the horizon signaled an approaching storm. The reappearance of specific stars indicated the time for planting crops. To mark these patterns, they created physical symbols and developed rituals to preserve their significance. Over centuries and millennia, their understanding deepened. They uncovered hidden laws governing nature, reaching far beyond the visible world and the limits of common sense. They discovered principles that held true throughout the cosmos, equations that dictated physical phenomena, irrespective of space or time. They unraveled the fundamental building blocks of matter, breaking elements into atoms, atoms into particles, and particles into subatomic components. They mastered the forces of gravity and quantum mechanics, delving into intricate mathematics that revealed the behavior of both microscopic particles and colossal galactic structures. They deciphered the mechanisms behind stellar fusion, supernova, and biological processes such as heartbeats and sensory perception. Their knowledge propelled them forward at an accelerating pace, surpassing the wildest dreams of their ancestors. Science became their most powerful tool, elegant, boundless, and beautiful. But this was only the beginning. How far could they extend their discoveries? How long would it take to reach Kardashev Type 1 status? Nikolai Kardashev never set out to define the scales of advanced civilizations. His aspiration was simply to be an astronomer. Born in 1932 in the Soviet Union, he faced immense hardships. His parents, once Communist Party members, were arrested when he was just 5 years old. His father was executed, and his mother was sent to a labor camp. Orphaned, Kardashev pursued his education, graduating before his mother was ever released. At Moscow State University, he specialized in radio astronomy, an emerging and exciting field at the time. His scientific career was prolific. He joined the Space Research Institute in 1967 and played a key role in the International Astronomical Union, fostering collaboration among scientists despite the tensions of the Cold War. However, Kardashev's lasting legacy emerged from a conference in Armenia in 1964, where he presented a groundbreaking paper on extraterrestrial communication. To estimate a civilization's ability to transmit radio signals, he proposed a simple yet profound idea. More advanced civilizations would harness exponentially greater amounts of energy. He likened the progression from early humans gathering around campfires to modern society splitting atoms for power. Kardashev hypothesized that sufficiently advanced civilizations would eventually capture the energy output of an entire star, or even an entire galaxy, enabling them to communicate across cosmic distances. From this, he devised what became known as the Kardashev scale. A Type 1 civilization would harness the full energy potential of its home planet. A Type 2 civilization would utilize the energy of its entire star. A Type 3 civilization would command the energy of an entire galaxy. After delivering his paper, Kardashev returned to his primary passion, astronomy. But the public's fascination with his scale endured, sparking imaginations for generations to come. Yet before one can dream of intergalactic empires or the ultimate frontiers of scientific progress, one must remember where the journey began: survival. Humanity arose in a world that was unpredictable, complex, and perilous. Our greatest asset was our capacity to learn, to think critically, to envision possibilities beyond the immediate, and to make deliberate choices based on reason. Science became our most vital weapon. One of the earliest recorded instances of scientific thought is found in a small ivory tablet, dating back over 32,500 years. One side of the tablet bears the carved silhouette of a figure resembling the constellation Orion, one of the most widely recognized star formations across cultures. The other side features 86 precisely etched notches. 86 is an intriguing number. From the vantage point of the cave where the tablet was found, Orion remained below the horizon for approximately 86 days each winter. Subtracting 86 days from a full year yields a rough estimate of the human gestation period. Could these ancient people have devised a method to track time based on Orion's disappearance and reappearance? And had they connected this cycle to the length of pregnancy? Their exact motivations remain a mystery, but one thing is certain: they had embarked on a journey toward scientific understanding. Galileo once stated, "The book of nature is written in the language of mathematics, and its symbols are triangles, circles, and other geometric figures. Without these, it is impossible to comprehend even a single word. Without them, one wanders aimlessly through a dark labyrinth." He was among the first to apply mathematics to uncover truths about nature that defied common sense. For instance, intuition suggests that heavier objects should fall faster than lighter ones, an idea supported by the philosopher Aristotle, who believed that heavier objects had a stronger affinity for Earth. However, through mathematical reasoning and meticulous experimentation, Galileo demonstrated that all objects fall at the same rate, except when air resistance interferes. This revelation marked the dawn of modern science, where observation and empirical evidence guide the pursuit of knowledge. A fundamental principle of science is that ideas and theories, no matter how appealing, must ultimately be tested and validated through evidence. Mathematics provides science with two essential tools. First, mathematical models offer concise, efficient representations of natural phenomena. After all, E equals mc squared is far easier to remember than a lengthy explanation. Second, mathematics enables scientists to logically develop hypotheses and predict their consequences with certainty. A fitting example of this can be found in the study of lightning. For thousands of years, the true nature of lightning was the subject of philosophical debate. Many cultures viewed it as a sign of divine will, often an expression of wrath. The ancient Greeks had observed certain electrical phenomena, such as the sparks produced when rubbing amber against cloth. Indeed, the word electricity derives from the Greek word for amber. Some philosophers speculated that lightning was an amplified version of this static electricity, while others believed it was a form of fire. The mystery remained unsolved until 1752, when Benjamin Franklin conducted his famous kite experiment during a thunderstorm. By capturing electrical current from the storm into a Leyden jar, a primitive type of battery, he provided definitive proof that lightning was indeed electricity. This discovery paved the way for further breakthroughs. Scientists like Charles Augustin de Coulomb formulated fundamental laws governing electrical charge, while mathematical insights from Carl Friedrich Gauss and Michael Faraday led to the concept of electric fields. Later, James Clerk Maxwell unified electricity and magnetism, demonstrating that light itself was composed of electromagnetic waves. This chain of reasoning, careful experimentation, and mathematical innovation transformed our understanding of lightning, and ultimately the very nature of light, an outcome few could have anticipated. Through the scientific method, humanity has unraveled countless natural mysteries. Storms arise from the movement of heat in the atmosphere, volcanoes result from magma eruptions, lightning is a discharge of static electricity, and diseases are caused by microscopic pathogens. Our understanding of the universe is constantly evolving. Gravity, for instance, has undergone multiple revisions. Galileo laid the groundwork, followed by Newton, who recognized gravity as a universal force governing celestial bodies. Then, centuries later, Einstein revolutionized our understanding once again, revealing gravity as the warping of space-time caused by mass and energy. Even today, scientists anticipate another major breakthrough, one that integrates quantum mechanics into the theory of gravity. In just a few centuries, science has propelled humanity further in knowledge and technological mastery than all previous millennia combined. Yet, for all our achievements, the universe remains an enigma, filled with questions we have yet to answer. How much can we truly know? Is there a limit to human understanding? One possible constraint is our own biology. Despite the sophistication of the human brain, it can only store and process a finite amount of information. Some individuals exhibit extraordinary memory or reading speeds, such as Emma Alam, who memorized 410 words in 15 minutes, or Rajveer Meena, who recalled 70,000 digits of pi. But even the most advanced minds are bound by physical limits. While the human brain's memory capacity is estimated to be around 2.5 petabytes, this is still small compared to the vast data processing power of supercomputers. Beyond cognitive constraints, our physical fragility is another limitation. We require food, water, and sleep. Records suggest the longest anyone has remained awake is about 19 days. Our existence depends on delicate biological processes. Electrical impulses travel through neurons, hormones regulate homeostasis, and proteins facilitate energy storage and release. These mechanisms, shaped by billions of years of evolution, cannot easily be altered. As a result, we remain tethered to Earth's biosphere, unable to survive without artificial support in space. This raises an important question. Is it possible to transcend the limitations of our biological form? A civilization had reached the pinnacle of technological advancement, spending a millennium constructing an unprecedented scientific experiment. Having achieved what we would classify as a Kardashev Type 1 civilization, they harnessed energy on a planetary scale. Solar panels encircled their star, fusion reactors generated immense power, and their colonies spread across the solar system, from sun-scorched worlds to frozen moons. Their robotic explorers ventured into the interstellar void. They had uncovered the fundamental laws of physics, including quantum mechanics, and harnessed these insights to build seemingly magical devices. But even at the peak of their knowledge, they encountered limits. They had long known that nature's fundamental forces unify at incomprehensibly high energies beyond the reach of any planetary laboratory. To probe deeper, they constructed a particle accelerator the size of their solar system. They scavenged asteroids and stripped layers from uninhabited moons to assemble a vast ring of superconducting tunnels encircling their star. According to their calculations, this immense collider would generate energies capable of breaching the quantum gravitational threshold, accessing the Planck scale, where the fabric of space and time itself begins to unravel. Over centuries, the experiment became more than science. It took on the weight of mythology. The inaugural test of the collider was not just an academic milestone. It was a moment of profound significance, marked by elaborate ceremonies, grand speeches, and solemn rituals. At long last, after countless generations of effort and anticipation, they initiated the experiment, eager to uncover the very essence of nature itself. The human brain, composed of approximately 100 billion neurons and 100 trillion synaptic connections, stands as the most intricate structure known to exist. Our unparalleled ability to absorb, process, categorize, and prioritize information sets us apart from all other living beings. Yet, as our curiosity remained insatiable, we devised tools to extend and enhance our cognitive capabilities. Before the advent of germ theory, physicians believed that cholera, a devastating disease causing severe dehydration and diarrhea, stemmed from miasma, or bad air. However, in the mid-1800s, physician John Snow suspected otherwise, but lacked the means to prove it. When a cholera outbreak struck London's Soho district in 1854, he employed a relatively novel method, a simple dot map, to track and visualize case clusters. This rudimentary yet effective tool led him to identify the source, a water pump on Broad Street. Armed with this evidence, he persuaded local authorities to remove the pump's handle, effectively ending the outbreak. His brilliant use of a basic map ultimately saved countless lives. This case demonstrates that technological advancements do not need to be complex to be impactful. However, as our understanding of the natural world deepened, we developed more sophisticated instruments to probe further and uncover even more. We designed tools to enhance our senses, beginning with the telescope, a simple market novelty transformed into a scientific device by Galileo. His first telescope, capable of only 8 times magnification, inferior even to modern binoculars, nonetheless revealed breathtaking discoveries. The moon's mountainous surface, Jupiter's moons, Venus's phases, and the vast star clusters comprising the Milky Way. Each successive telescope led to even greater revelations, culminating in the 1920s with the Hooker telescope, which allowed Edwin Hubble to identify pulsating stars in the Andromeda Nebula, proving it was in fact a distant galaxy millions of light years away. As telescopes grew larger, some now exceeding 30 meters in diameter, ground-based observations faced atmospheric distortion limitations. Space telescopes, though smaller, provided clearer views of the universe. The James Webb Space Telescope, with its 6.5 meter mirror, so large it had to be ingeniously folded for launch, achieves an astonishing resolution of about 1/10 of an arcsecond, hundreds of times more precise than human vision, capable of discerning the details of a coin from 40 kilometers away. Looking ahead, one of the most ambitious telescope concepts is the Solar Gravitational Lens. By exploiting the sun's gravitational field, an instrument positioned approximately 540 astronomical units away could attain a resolution of 10 to the negative 10th power arcseconds, offering the potential to capture highly detailed images of exoplanets within a 100 light-year radius. On the microscopic scale, we developed instruments to unveil the hidden world beneath our perception. The most advanced modern microscopes utilize quantum tunneling to achieve resolutions as fine as 0.05 nanometers, allowing scientists to map atomic and molecular structures and capture intricate images of even the tiniest biological entities. Most recently, computing has emerged as a third branch of scientific inquiry, standing alongside theoretical work and physical experimentation. Highly sophisticated computer algorithms now simulate complex natural processes, tracing their evolution as they adhere to the fundamental laws of physics. Through simulations, we have watched virtual universes unfold over billions of years, examined the fiery deaths of stars and supernova explosions, and unraveled the intricate mechanisms of protein folding. Over the 20th century, technology advanced at an unprecedented pace, fueling humanity's relentless quest for knowledge. Today, the total volume of electronically stored human knowledge is estimated at approximately 175 zettabytes, or 175 trillion gigabytes. Each year, global energy consumption reaches nearly 5 times 10 to the 20th power joules. While only a fraction of this energy is devoted to storing information, expanding our technological reach and acquiring further knowledge will inevitably require far greater energy resources. This raises a crucial question. What is the most efficient way to obtain more energy? If we were to blanket the entire Earth with solar panels, we could harness approximately 4.4 times 10 to the power of 16 joules of solar energy per second, enough to satisfy current global energy demands for an entire year in less than 3 hours. However, to push beyond current limitations, we would need to either capture more solar energy or seek alternative energy sources within the cosmos. One possibility proposed by physicist Freeman Dyson is the construction of a Dyson sphere, a vast artificial shell surrounding the sun, designed to capture a significant portion of its emitted energy. By dismantling entire planets and repurposing their material into kilometer-thick solar panels, we could theoretically capture 0.0 0.0004% of the sun's total output, an immense increase compared to the tiny fraction of solar energy that currently reaches Earth. Yet such mega engineering projects come with substantial energy costs. The sheer amount of energy required to disassemble a planet and convert it into a Dyson sphere would take tens of thousands of years to recover. The absence of observable Dyson spheres in the galaxy suggests that civilizations may have opted for alternative strategies. One such alternative could involve tapping into the rotational energy of black holes. These cosmic giants, due to their intense gravitational pull and rapid spinning motion, create distortions in space-time that advanced civilizations might exploit using mechanisms such as the Penrose process. Harnessing such power sources could allow species to transform entire planets into data storage facilities, convert entire solar systems into vast observatories, and send interstellar probes to the edges of the galaxy. The pursuit of higher energy levels also plays a fundamental role in humanity's ongoing attempts to unravel the deepest mysteries of reality, particularly through high-energy physics. Since the 1930s, scientists have used electric and magnetic fields to accelerate charged particles to extreme velocities before smashing them together, analyzing the resulting debris to uncover the fundamental building blocks of matter. One of the pioneers of this technique, Ernest Lawrence, built a 4-inch cyclotron capable of reaching energies of 80,000 electron volts. After World War II, particle physics surged forward, leading to the creation of the Cosmotron at Brookhaven National Laboratory in New York, which achieved 3.3 billion electron volts and led to the discovery of mesons. Later, Fermilab's Tevatron in Illinois reached 980 billion electron volts, confirming the existence of the top quark in the 1990s. A proposed superconducting supercollider in Texas, which would have dwarfed all previous colliders, was ultimately abandoned due to budget constraints. Instead, the title of the world's most powerful particle accelerator belongs to the Large Hadron Collider, LHC, at CERN, straddling the border between Switzerland and France. Taking nearly a decade to construct at a cost of nearly $5 billion, the LHC achieves collision energies of up to 14 trillion electron volts. Thousands of scientists worldwide contribute to experiments at the LHC, which has played a pivotal role in confirming the standard model of particle physics, most notably by verifying the existence of the Higgs boson. However, even the LHC highlights the limitations of our current technology. To experimentally probe the Planck scale, the domain where quantum gravity effects become significant, would require a particle collider with energy levels 10 trillion times greater than what we can currently achieve. Thus, despite our technological progress, we are already confronting our own constraints. If we wish to continue pushing the boundaries of knowledge, we face an immense challenge. We must conceive entirely new technologies that surpass anything presently imaginable. Our engineering prowess must expand beyond planetary and stellar scales to encompass entire galaxies. A vast fleet of over 10,000 spacecraft set out on their journey. After countless generations spent refining ideas, analyzing various methods, and exhausting all possibilities, the civilization ultimately reached a conclusion. There was no single best way to explore the stars. So they pursued all approaches simultaneously. Some factions constructed massive generation ships, self-sufficient miniature worlds designed to sustain entire populations for thousands of years. Others developed agile single-passenger crafts, propelled by powerful beams of light from planetary stations to send them toward distant stars. The majority, however, opted for a compromise: medium-sized vessels carrying a substantial, yet not overwhelming, number of travelers. Most of the passengers remained in a state of deep sleep, while automated systems guided their ships. The Endeavour demanded nearly all of the civilization's resources, but they had little choice. Their home system's energy and materials had been depleted. The search for answers and survival compelled them to venture outward. They had surpassed the limits of a Kardashev Type 1 civilization, and were now poised to push toward Type 2 and beyond. Surprisingly, the key to unlocking interstellar travel lay in an unexpected source: hummingbirds. With over 100 known species, hummingbirds are among the tiniest birds on Earth. Most reside in the lush tropical rainforest year-round, but some species migrate vast distances each year. One such species, the rufous hummingbird, measuring just 7 centimeters in length, embarks on an astonishing 6,000-kilometer journey from Alaska to Mexico every winter, only to return each spring. One of the hummingbird's key survival strategies is torpor, a hibernation-like state in which the bird reduces its body temperature by half and slows its metabolism by 90%. This energy-conserving ability would be crucial for humans if we ever hope to cross the vast distances between the stars. Voyager 1, launched in 1977, is currently over 25 billion kilometers from Earth, making it humanity's most distant spacecraft. It has already crossed into interstellar space, passing the heliopause in 2012, where the sun's influence gives way to the interstellar medium. However, even at its current speed of over 60,000 kilometers per hour, Voyager 1 will take thousands of years just to reach the outer edges of the Oort cloud, the distant region of icy debris at the farthest reaches of our solar system. If it were headed toward Proxima Centauri, our closest neighboring star, it would still take more than 35,000 years to arrive. Though we are growing accustomed to interplanetary travel, venturing beyond our solar system is an entirely different challenge. The nearest galaxy, the Canis Major Dwarf Galaxy, is an unfathomable 25,000 light-years away. At Voyager's speed, it would take roughly 749 million years to reach it. Current spacecraft receive most of their acceleration at launch, with additional minor boosts from planetary gravity assists. However, in the vastness of interstellar space, gravitational slingshots are not an option, making propulsion a significant challenge. In theory, we have two main options: build massive but slow-moving ships capable of sustaining life for generations, or develop smaller, high-speed crafts to shorten the journey. During the 1950s and 60s, scientists explored one of the most extreme propulsion methods: nuclear explosion-driven spacecraft. Project Orion proposed using controlled nuclear detonations behind a spacecraft to push it forward. Estimates suggested that a 10,000-ton ship could reach Mars with just 800 detonations, or Saturn in under 3 years. While the concept showed promise, technical and political challenges ultimately led to its abandonment. However, future generations may revisit this idea or devise new, more efficient propulsion systems to reach the stars. An alternative method, popular in science fiction, is the Generation Ship, also called a world ship or ark. Instead of striving for high speeds, these colossal vessels would function as self-sustaining floating habitats, where multiple generations of humans would live and die before their descendants finally reached another star. Although such a voyage would be perilous and require highly advanced technology, even slow, incremental expansion could eventually lead to the colonization of hundreds of worlds. A civilization determined to explore interstellar space might not even need to build such ships from scratch. Natural objects, like interstellar asteroids and comets, already drift between solar systems. In 2017, one such object, Oumuamua, briefly passed through our solar system before vanishing into the depths of space. A patient and resourceful species might one day find a way to hitch a ride, transforming a wandering space rock into a mobile habitat for their journey across the stars. The only currently known way to speed up interstellar travel is to make the spacecraft as small and lightweight as possible, enabling it to reach higher velocities with the available propulsion energy. In recent years, the Breakthrough Starshot Initiative, based in New York, has proposed such a solution. This concept relies on a light sail, a thin reflective membrane that captures the force of light to propel the craft forward. The proposed Starshot design features a square light sail spanning a kilometer on each side, propelled by a 100 gigawatt laser for a duration of 10 minutes. This immense burst of energy could push the spacecraft to 10% the speed of light, allowing it to reach the closest neighboring star system within a human lifetime. However, there is a significant limitation. The entire spacecraft must weigh no more than a gram, roughly the weight of a paperclip. Unless an advanced civilization aims to scatter paperclips across the galaxy, they will need to develop more effective methods of travel. Thus, how far an ambitious species could truly go remains uncertain. A few light years would be enough to explore nearby stars, while traveling tens of thousands of light years would allow them to traverse an entire galaxy. Expanding into distances spanning millions of light years could enable them to leap between galaxies themselves. Despite the immense challenges, if such a civilization were able to achieve near-light speeds, the laws of physics offer them an unexpected advantage: time dilation. One of the fundamental principles of relativity states that moving clocks run slower, meaning that, from the perspective of an outside observer, an object approaching the speed of light experiences time at a much slower rate. Space and time are deeply intertwined, and for travelers moving at extreme speeds, time passes normally from their own perspective, even as the rest of the universe appears to speed past them. To make use of this effect in a meaningful way, however, a spacecraft would need to reach a significant fraction of the speed of light, which presents substantial technical and energy-related challenges. If a civilization could somehow harness the required energy, they could theoretically reach distant regions of the galaxy within the span of their own lifetimes. For instance, if a spacecraft could maintain a constant acceleration of 1g, roughly 10 meters per second squared, steadily increasing its velocity toward the speed of light. The journey from our solar system to the Milky Way's galactic core would take nearly 30,000 years, as observed from an outside perspective. However, for passengers aboard the ship, the entire trip would be experienced in only a few years of ship time due to the effects of relativity. This is an extreme case, requiring immense energy resources, but it highlights a fundamental reality. To explore the broader universe, humanity may need to radically alter our biology and extend our lifespans. At present, humans live for approximately 80 years, a fleeting moment on cosmic timescales. While cultural traditions and written records allow us to pass knowledge across generations, they are insufficient for direct long-term exploration of interstellar space. If we wish to unravel the greatest cosmic mysteries and harness the universe's vast energy reserves, we will need to find ways to enhance both our cognitive abilities and longevity. Perhaps the most effective path forward will be to free human consciousness from biological constraints. If we can develop systems that allow our minds to exist independently of the physical body, we could explore the cosmos without relying on oxygen, water, food, or other critical resources. Advanced spacecraft might carry individuals, or even entire societies, preserved in low-energy, hibernation-like states, awakening only when necessary resources become available. This would not be artificial intelligence in the traditional sense, but rather synthetically sustained organic intelligence. Even with such advancements, there may still be ultimate barriers. At the end of the day, we all exist within the same universe, governed by the same physical laws. No matter how advanced a civilization becomes, cosmic constraints impose fundamental limits on how far we could ever go. They simply called it the machine. Its construction spanned countless generations, so long that the original architects, and even the planet on which they conceived the idea, had faded from history. Yet, the purpose of the machine remained unchanged, surviving through wars, political upheavals, and eras of peace. This civilization had long since mastered space travel. They had built starfaring vessels, controlled the force of gravity, and created artificial intelligences as sentient as themselves. They had reached Kardashev Type 2 status, harnessing the total energy output of entire stars using colossal networks of solar panels. But the machine was their most ambitious project yet. Their probes had explored the vastness of their home galaxy, yet they found no trace of any other life. Were they alone? Was the universe meant solely for them? A faction of scientists devised a bold plan. They would conduct a complete survey of every galaxy in the entire observable universe. The machine spanned their entire galaxy. Automated missions restructured distant solar systems, converting planets into lenses, antennas, power stations, and data hubs. Each system transformed into a vast observatory. The process took 10,000 years per survey, and when complete, the data was transmitted back home before each observatory dismantled itself. The information traveled across space for over 100,000 years. Entire planets were repurposed into colossal data storage facilities, and black holes provided the power needed for computation. This was the ultimate goal, to catalog everything, to answer every question the universe had to offer. Only then could their civilization truly rest. If we project humanity's technological progress far into the future, assuming we continue advancing at an exponential pace, we can imagine achieving incredible feats. Particle accelerators encircling the entire solar system, reaching energies far beyond those of today's Large Hadron Collider. Telescopes positioned in the outer solar system, using the sun's gravitational lensing to magnify distant celestial objects. Megastructures that harness energy from neutron stars and black holes, unlocking unimaginable computational power, perhaps even simulating the universe itself. Yet, no matter how advanced we become, there are fundamental limits we cannot overcome. The universe has hard boundaries, constraints imposed by the speed of light, the finite number of particles, and the relentless march of entropy. At some point, if our quest for knowledge continues indefinitely, we will eventually exhaust all available information. In the 1920s, Edwin Hubble discovered that the universe is expanding. Nearly every galaxy is moving away from every other, driven apart by the fabric of space itself. This expansion introduced two profound limitations: a finite age. Prior to Hubble's findings, many assumed the universe had existed eternally. The Big Bang Theory shattered this notion, placing a definite beginning, 13.77 billion years ago, on our observable universe. A limited reach. While the universe may be infinitely vast, our ability to observe it is restricted. Light can only travel so far in a finite time, meaning we see only a small fraction of existence, like a flashlight cutting through the darkness. And so, no matter how much we learn, The final, unavoidable truth is this: there's only a finite amount of knowledge in the universe. One day we may reach the cosmic limit, where no further mysteries remain to uncover. And when that day arrives, what will we do next? This constraint is encapsulated by the concept of the light cone, a representation of the limits governing the spread of influence and information across both space and time. For instance, when a light signal is emitted, it requires time to traverse vast distances. If the sun were to suddenly cease shining, it would take approximately 8 minutes for Earth to experience the ensuing darkness. Likewise, if the Andromeda Galaxy were to mysteriously vanish at this moment, its absence would remain undetectable to us for another 2.5 million years. Applying this principle to the entire universe suggests that the cosmos extends far beyond what we could ever observe. This implies the existence of galaxies, stars, and cosmic events, whose information will forever be beyond our reach. Their light will never reach us, and whatever mysteries they conceal will remain forever hidden. In fact, due to the continuous expansion of the universe, the most distant objects within our observable limits are already moving away faster than the speed of light. The light we currently see from these galaxies was emitted billions of years ago, and by now, they have receded so far that over time, they will eventually disappear from view. As the universe expands, the portion of it that remains observable gradually shrinks. Consequently, all the information we could ever acquire about the cosmos is confined within these boundaries, approximately 14 billion years into the past, and around 42 billion light years in any direction. This limitation introduces an inherent uncertainty in large-scale measurements, known as cosmic variance. Many phenomena in the universe are influenced by random chance, shaped by fundamental physics, yet developing through unpredictable processes. For example, the Milky Way occupies a specific position in space with unique characteristics: its mass, star formation rate, and history of galactic mergers. However, the physics governing the early universe only set the conditions for galaxy formation. They did not predetermine where each galaxy would emerge. In theory, the Milky Way could have formed in any location. When measuring large-scale cosmic structures, or fundamental constants such as the total amounts of dark matter or dark energy, this randomness must be factored in. Since we can only study a limited portion of the universe rather than its entirety, there will always be a degree of uncertainty. Imagine being shown only a handful of cards from a full deck. You would never be able to determine with absolute certainty how many of each suit exist. Similarly, our observations of the universe will always be constrained by this unavoidable limitation. While these restrictions exist on the largest scales, a very different type of uncertainty emerges at the opposite end of the measurement spectrum, the realm of quantum mechanics. One of the most fundamental limits in physics is the Heisenberg uncertainty principle. Discovered in 1927 by Werner Heisenberg, it was initially viewed as a limitation of experimental techniques. To observe a subatomic particle, one must interact with it, typically by bouncing photons off it. In the macroscopic world, this interaction is negligible. A bright light does not affect the motion of a charging bear. However, at the quantum level, photons carry enough energy to disturb tiny particles. If a scientist wishes to precisely determine the position of a particle, they must use a photon with an extremely short wavelength, which means it carries high energy. But upon striking the particle, this high-energy photon alters its motion, making it impossible to accurately measure its velocity. Conversely, using a low-energy photon ensures minimal disturbance, but its longer wavelength reduces precision in locating the particle. Heisenberg realized that it was fundamentally impossible to measure both a particle's position and momentum with perfect accuracy. This was not merely a technological limitation, it was a fundamental aspect of quantum mechanics. Despite numerous attempts to disprove the uncertainty principle, even Albert Einstein was unable to do so. Throughout a series of debates with Niels Bohr, Einstein proposed various thought experiments to demonstrate that the uncertainty was an illusion caused by our incomplete understanding of quantum physics. However, Bohr systematically identified flaws in Einstein's reasoning, showing that the uncertainty was an unavoidable feature of reality. While Einstein reluctantly conceded that limits to knowledge existed, he remained convinced that quantum mechanics was an incomplete description of nature. Thus, the quantum world contains information that remains fundamentally inaccessible. One manifestation of this limitation is the inherent probabilistic nature of quantum processes. In classical physics, if one knows the exact state of a system, including the positions and velocities of all particles, its future evolution can be predicted with absolute certainty. Quantum mechanics, however, does not adhere to this deterministic framework. Instead, even with complete knowledge of a quantum system's state, one can only predict probabilities of future outcomes. The Schrödinger equation provides the mathematical framework for calculating these probabilities, Every particle in the universe is associated with a wave, which represents its probability distribution. Where the wave is most pronounced, there is a higher likelihood of detecting the particle. Where it diminishes, the probability decreases. This wave does not reveal the exact location of a particle, only the likelihood of where it might be found. Surprisingly, quantum effects are not always confined to the microscopic realm. In 2019, a research team led by Jakob Fein at the University of Vienna demonstrated quantum behavior on an unprecedented scale. They successfully observed wave-like properties in a molecule containing over 2,000 atoms, an enormous leap from single-particle quantum experiments. Their findings suggest that, under the right conditions, quantum uncertainty can manifest at much larger scales than previously thought. Beyond quantum mechanics, there exist other places where knowledge remains permanently inaccessible, inside black holes and within the past itself. Black holes represent the ultimate vaults of information, containing the densest possible concentration of knowledge in the universe. However, virtually none of it can be retrieved. The defining feature of a black hole is its event horizon, a boundary that prevents anything from escaping once it crosses over. Everything that has ever fallen into a black hole, including the material that initially formed it, is hidden behind this veil. One could theoretically access this information by entering a black hole, but this would come at a terrible cost. Any observer who crosses the event horizon can continue receiving information from the outside universe, but they will never be able to send messages back. Furthermore, once inside, their fate is sealed. In a finite amount of time, measured by a watch on their wrist, they are destined to reach the singularity, the point of infinite density at the core of the black hole. Whatever knowledge they might uncover would be forever lost to the rest of the universe. Any knowledge gained from delving into the core of a black hole perishes with the one who acquires it. All that remains visible to the outside universe are three defining attributes: mass, angular momentum, and charge. Beyond these, everything is obscured in darkness. Regarding the past, as far as our understanding of physics and the fundamental principles of space, time, and causality allow, what has transpired is permanently lost, beyond our reach, except through memories, artifacts, and the present state of existence. We can theorize, speculate, and analyze endlessly, but the moment an event passes, it vanishes behind an unyielding horizon. What is not recorded is truly gone. Across vast cosmic scales and microscopic realms, through imperceptible boundaries and unfathomable passageways, there exist entire domains of the universe that will forever remain inaccessible to us. This raises the ultimate question: what are the absolute limits of the knowledge we can attain? What is the fundamental boundary of cosmic understanding? In the observable universe, estimates suggest there are between 500 billion and 2 trillion galaxies. If we could somehow halt the expansion of space and instantaneously document every single one, that would define the totality of galaxies available for study. Any inquiry regarding galactic evolution would be confined to that data set. These galaxies contain an estimated 200 billion trillion stars. If we meticulously cataloged each of them, measuring their position, velocity, spectrum, and other properties, we would inevitably reach a point where questions arise that surpass our available data. Shifting our focus to microscopic scales, we might attempt to extract even greater insight from the universe. The observable cosmos contains approximately 10 to the power of 80 protons. In theory, we could determine the precise location, momentum, and quantum state of every one of them, extending this effort to electrons, neutrinos, dark matter particles, and beyond. Completing this exercise would require measuring the properties of approximately 10 to the power of 90 photons, most of which originated from the cosmic microwave background. The afterglow of the universe's transition from a hot, dense plasma to a neutral state 380,000 years after the Big Bang. Each of these particles carries a finite amount of information, but even this exhaustive catalog would not represent the ultimate limit of knowledge. The fundamental reason is that all particles emerge from quantum fields, which manifest as vibrations within space-time itself. These fluctuations exist regardless of whether a particle is present or not, meaning that true comprehension requires probing beyond particles to the fabric of reality itself. As we analyze smaller and smaller regions, accumulating information at each step, we ultimately encounter the constraints imposed by Heisenberg's uncertainty principle, the realm of quantum foam. Quantum foam can be perceived in two ways. One perspective suggests that quantum fields momentarily borrow energy from the vacuum of space-time, creating transient particles before returning the energy unnoticed. Another interpretation posits that quantum fields possess an inherent baseline energy, a fundamental vibration permeating even the emptiest void. The limit of this realm is defined by the Planck length, approximately 1.61 times 10 to the negative 35th meters, a scale derived from fundamental constants such as the speed of light, the gravitational constant, and Planck's constant. At this boundary, the conventional notions of space and time dissolve into a turbulent sea of fluctuations. While knowledge may exist at even smaller scales, it lies beyond the reach of known physics, making the Planck length the ultimate resolution threshold for accessible information. To estimate the total information content of the universe, we can divide its observable volume into minuscule Planck scale units, each representing a fundamental quantum state. Advanced physical theories linking entropy with information through the work of Claude Shannon suggest that the universe's total information capacity can be approximated by assigning a single bit to each Planck scale region. This leads to an estimated information limit of about 10 to the 120th power bits. Though speculative, this boundary, no matter the approach, represents an ultimate constraint on knowledge. No matter how advanced civilization becomes, these limits cannot be surpassed. Yet even if we were to accumulate all possible knowledge, uncover every hidden truth, and measure every observable quantity, would we still be missing something? Is there an alternative way to comprehend the universe? When first proposed, the idea was terrifying. It was met with fierce resistance, dismissed as nonsense, and outright banned. To the civilization, in all its vast and diverse forms, it was a heretical notion, an affront to everything they had ever cherished. But as time marched on and no new paths to knowledge emerged, the idea grew more alluring, more irresistible. By this era, the civilization had become ancient beyond reckoning. They had long since abandoned their homeworld, transcending even planetary existence. They spread across the entirety of their galaxy, reshaping and mastering it to their will, having found no other intelligent life within. As a Kardashev, Type 3 civilization, they harnessed the full energy output of their galaxy. Yet despite their immense advancements, they encountered barriers they could not breach. One such limit was themselves. No matter how far they advanced, they remained bound by the constraints of their own minds. They could not conceive of existence in any form other than their own. Were their thoughts, as sophisticated as they had become, still constrained by the genetic imprints of their ancient past? Could it be that their understanding of the cosmos was fundamentally restricted by their biology? To overcome this, they created machines that could think for themselves, hoping artificial intelligences might surpass them, perceiving reality in ways beyond their own limitations. But these machines, no matter how powerful, were merely reflections. Faster, different, sometimes alien in thought, but ultimately the same. And so, in their desperation, a radical idea took shape. They identified a young planet, hidden in an unremarkable corner of their galaxy, a world abundant in water, orbiting a stable star, rich in the elements needed for life. They intervened subtly, adjusting conditions with delicate precision. A nudge here, a modification there, just enough to steer the chaotic dance of molecules toward a specific outcome. But this was not a mere experiment in biology. Encoded within the chemistry of that emerging life were the seeds of intelligence. They did not know what kind of minds would arise. That was the entire point. These future beings, unpredictable, shaped by an entirely different evolutionary path, would see the universe in ways the architects of the experiment could not. They would develop new perspectives, uncovering truths their creators had become blind to. Their very existence would be an experiment in perception. Satisfied, the civilization withdrew. They slept, dreaming of the knowledge these new beings would one day uncover. There may be fundamental limits to how we acquire knowledge within the universe. Even science, for all its power and flexibility, may not be the ultimate tool for extracting every last fragment of information. Before the scientific method, humans gathered knowledge through intuition, experience, and philosophy. Science itself is an outgrowth of philosophy, which has long questioned the nature of knowing. Mathematics, another discipline, explores abstract logical structures that remain true regardless of their physical applicability. Skepticism challenges whether we are truly uncovering objective truths, or merely constructing narratives that fit our perceptions. Even within the natural world, some questions may forever elude us. The nature of time, the enigma of consciousness, the sheer existence of the universe itself, these mysteries persist beyond our grasp. Perhaps our understanding is confined not by the laws of physics, but by the very structure of our minds. One possibility is artificial intelligence. If intelligence is a universal trait, then an advanced AI might simply be a different variation of our own cognition. But what if machine intelligence is something entirely alien? Not merely superior in processing speed or problem-solving ability, but fundamentally different in perception and thought? This debate has intensified with the rise of generative AI, like ChatGPT. These models construct sentences based on statistical probabilities, mimicking human language without true comprehension. They do not think in the way we do, yet they exhibit a peculiar form of intelligence, one unfamiliar, perhaps even incomprehensible to us. Could such minds unlock knowledge beyond our reach, or will they too encounter the same limits? Some argue that continued advancements in artificial intelligence could give rise to a fundamentally different form of intelligence, one capable of reasoning and comprehension but structured upon entirely distinct cognitive frameworks. A sufficiently advanced AI might uncover profound truths about the universe, insights so intricate that it would be incapable of conveying them to us, as our human minds are constrained to operate within a singular, limited mode of understanding. However, there is also the possibility that such artificial intelligences, despite their sophistication, would remain confined by the limitations of their creators, trapped within the boundaries we unknowingly impose upon them. And even if we were able to answer these profound questions, everyone we have considered and even those yet to be conceived, even if we could access the entirety of the universe, free from any bias or biological constraint, even if we could examine reality from a completely different perspective, one insurmountable barrier would still remain: infinity. The earliest recorded philosopher to engage with the notion of infinity was Anaximander, a Greek thinker from around 600 BCE. He proposed that the universe was boundless, or indefinite, a concept that today aligns with our understanding of infinity. Later, Indian philosophers such as those in the Surya Prajnapti tradition explored different magnitudes of infinity, suggesting that an infinite line was lesser than an infinite plane, which in turn was surpassed by an infinite volume, all of which were inferior to an infinite dimensional expanse. However, Greek philosophers who followed rejected the notion of infinity, arguing that its existence led to logical paradoxes. Zeno of Elea, for instance, questioned the nature of motion. If one continuously halves the remaining distance to a destination, can one ever truly arrive? Despite such philosophical debates, infinity proved indispensable in mathematics. In 1655, the English clergyman and mathematician John Wallis introduced the infinity symbol infinity, which remains in use today. The related concept of the infinitesimal became foundational in the work of Isaac Newton and Gottfried Leibniz, forming the basis of calculus. In modern mathematics, infinity is recognized as a broad and complex category, and thanks to the pioneering work of Georg Cantor in the late 19th century, we now understand that there are multiple types of infinity, indeed an infinite hierarchy of infinite numbers. Yet, while mathematics has embraced infinity, its presence in physics continues to disrupt our understanding of the universe. One of the most perplexing sources of this issue emerges from an unexpected place: the Big Bang. Our leading theory on the universe's earliest moments, known as cosmic inflation, describes a rapid expansion in a fraction of a second. Within this framework lies the intriguing possibility that our universe is just one of countless others, existing within a vast multiverse. Each universe could possess its own unique laws of physics, distinct particles, forces, and structures. If we take this idea to its extreme, then somewhere in the multiverse, there could exist an identical copy of you, reading these very words at this exact moment. In fact, due to the nature of infinity, there would be an infinite number of versions of you, watching an infinite number of variations of this scenario, all happening simultaneously. This leads to what is known as the measure problem. If there is an infinite number of universes beyond our reach, how can we meaningfully determine probabilities? How can we assess the rarity or commonality of any phenomenon? The problem arises because every conceivable universe would exist in infinite quantities. For any characteristic of our own cosmos, such as the prevalence of life, or the nature of dark energy, there would be an infinite number of universes both abundant in that trait and entirely devoid of it. Although advanced mathematical methods allow us to compare infinities, we do not yet know which principles, if any, apply to the multiverse. As a result, we find ourselves adrift in a sea of uncertainty. Even if we could gather all available data, from the dawn of the Big Bang to the furthest reaches of the observable universe, we would still be left in the dark about the true nature of reality beyond our cosmic horizon. If the multiverse exists, and its existence may forever remain beyond empirical proof, it imposes a stark limitation on our pursuit of knowledge. We may someday develop a new kind of physics, one that allows us to traverse between universes, unveiling the unimaginable variety the multiverse has to offer. We might encounter realms governed by exotic laws, far removed from our own. Yet, even this would not resolve the fundamental challenge posed by infinity. In an infinite cosmos, no matter how far we explore or how much we discover, there will always be an infinite number of unexplored universes just beyond our reach. No matter how much knowledge we acquire, it will always be a finite fraction of an infinite whole, effectively zero. The concept of an infinite multiverse may ultimately prove incorrect, but if it is true, it establishes the ultimate boundary of our knowledge. We may achieve total mastery over our own universe, but nothing beyond it. We may uncover every secret within our cosmic domain, but nothing further. Infinity remains an insurmountable force, too vast and overwhelming for us to ever fully comprehend. In our quest for knowledge, we face countless barriers. Our perceptions are limited by our biological senses, our imaginations, our intelligence, and even our modes of thought confine how we interpret reality. Technological constraints restrict our ability to probe the deepest microscopic and macroscopic scales. There may even be deeper, intrinsic limitations rooted in the very structure of our minds, shaped by our evolutionary past. Yet all of these obstacles are, in principle, surmountable. We can develop new ways of thinking, create ever more sophisticated technologies, and push beyond the frontiers of exploration. But despite our best efforts, we may eventually encounter the ultimate restriction, one imposed not by our ingenuity, but by the nature of reality itself. No matter how far we reach, we may never truly grasp everything.